Hello dear friends, welcome to a lecture on Euclidean ring. In this lecture we shall study greatest common divisor in Euclidean ring. First we shall define divisibility relation in a commutative ring. Earlier we have studied divisibility in number theory. There we have considered integers, and here we are considering elements of a commutative ring. And I have written here two definitions. First we shall see the definition, and then we will prove a result on greatest common divisor. The first definition is for divisor. If A is not equal to 0 and B are in a commutative ring, these are two elements of a commutative ring, A must be non-zero. Then we say A is A divides B. A is said to divide B means A divides B if there exists another integer C in R, another element C in R such that B is equal to A into C. That means if B is multiple of A, then we say A is divisor of B, and we write this relation as A divides B, and A is divisor of B or B is multiple of A. And for example, in number theory, in the set of integers, we can say 2 divides 6, because we can write 6 as there exists a C integer as 3, and we can write 6 as 2 into 3. So therefore 2 is divisor of 6. Similarly, 3 divides 15, etc. We know this relation in number theory, or that means taking integers. And these are some simple results. We have written this as a remark. First is, if A divides B and B divides C, then A divides C. This is obvious. If A divides B, we can write this as A divides B. This implies and implied by this B is multiple of A. Here we have written as a C, B is equal to A into C, but C is another element we have considered here, and therefore this we can write B is multiple of A means A into X for some X. And further, B divides C. B divides C, this implies C is multiple of B, and this can be written as C is equal to B into Y for some Y. And from this we can write C is multiple of A, because this C can be written as B into Y, where B is AX. So therefore it is A into X into Y. X into Y is an element of R and by closure property, and therefore C becomes multiple of A, or A is divisor of C. That is the first result. And second is, if A divides B and A divides C. See, A divides B implies A divides B implies B is multiple of A, that is B is equal to AX for some X in R. Similarly, A divides C, then this implies C is again multiple of A, that is C can be written as AY for some element Y in R. And now what we can write is B plus or minus C is equal to AX plus or minus A into Y, and that A is common, so we can write A into bracket X plus or minus Y, and this shows that certainly B plus or minus C is a multiple of A, and therefore A divides B plus minus C. That is the second result. And what about the third? All these results follows from the definition. This is the definition: A divide B if B is multiple of A. Now the next third is A divides B, then A divides B into X. See, this is obvious. A divides B, then this implies X is used here, so therefore we can write by according to definition B is multiple of A, that is A into C. B is equal to A into C. And if you multiply this by x, then this becomes Bx is equal to ACx. And we can write this in bracket, and this shows that A is divisor of Bx, or Bx is multiple of A, and that A divides B into x. Or in general, the result can be written as if A divides B. If A divides B and again A divides C, then this implies A divides the combination of B and C, that is Bx plus Cy for some xy belongs to R. All these are considered now as elements of a commutative ring R and not necessarily integers. Earlier we have studied then in number theory, we have only considered the integers, elements as integers, but here the elements are of a commutative ring R. So this is about divisibility relation, A divides B, if B is multiple of A, or B can be written as A into some element of R. Now the next definition is of greatest common divisor. You see, A, B are elements of commutative ring R, then D belongs to R is said to be a greatest common divisor of A and B if there are two conditions. The first is it must be a common divisor, and the second is it is greatest, it must be greatest. Now what is the condition for common divisor? It divides both. D is common divisor of A and B if D divides A and D divides B, that is first condition. And the second is whenever C is also a common divisor, C divides A and C divides B, then that C divides D, then D becomes greatest. So this is the these are the two conditions for greatest common divisor. Now for example, if you consider say for example of integers, we shall consider 12, A is 12 and suppose B is 20. Then what are the common divisors of 12 and 20? That we shall find. Divisors of 12. What are the divisors of 12? One is always a divisor. Then we will consider only positive integers. The negative integers are also divisor of these. And if you consider positive integers, then 12, the divisors, positive divisors of 12 are 1, 2, 3, 4, then 6 and again 12. These are the positive divisors. Because we are considering greatest common divisor, greatest divisor, and therefore we are taking only positive divisors. For 20, 1, 2, 3 is not, and 4 is, then 5, then 6, then 10, and further 20. So these are the divisors of 20. And now we see the common divisors of 20. Here we have 1 is common divisor always, and then 4 is common divisor. So the greatest is 4, and thus the GCD of 12 and 20, we write this by this symbol. GCD of 12 and 20 is 4. And now obviously these two conditions are satisfied, that this 4 divides 12 and 4 divides 20. Further, if another divisor is considered, you may see that 1 is also a divisor and 1 divides 4. If or the minus see 2 is also a divisor. 2 is also a divisor, a common divisor, but 2 is not the greatest, 4 is the greatest. The greatest common divisors are 1, 2, 4, and among these 4 is the greatest. So here 2 is a divisor, but 2 divides 4. C is common divisor, and that common divisor divides the greatest common divisor. So that's why D becomes greatest. So this is the condition for greatest, and this is the condition for common divisor. and next we write the greatest common divisor by this symbol. So this is the definition for greatest common divisor. Now we shall state an important result for common divisor, greatest common divisor, as a lemma. The greatest common divisor is expressed as combination of the two elements. The lemma is R be a Euclidean ring, then any two elements A and B in R have a greatest common divisor. There exists common divisor for any two integers, and that is one is necessarily a common divisor for any element. Unit element is a common divisor. So therefore common divisor exists always, and we denote the common divisor by D, or greatest common divisor by D. And further this greatest common divisor of A and B is expressed as combination of A and B. Lambda A plus mu B is combination of A and B for some lambda mu belongs to R. Lambda and mu are elements of R. A is multiplied by some another element of R as lambda, and B is multiplied by mu, and then its combination is lambda times A plus mu times B, and that is equal to D, or D is expressed as combination of A and B. For example, earlier we have seen the GCD of 12 and 20 is 4, because 4 divides 12, 4 divides 20, and 4 is the greatest common divisor. Now this 4 can be written as combination of 12 and 20, and that can be written in different way. We can multiply 12 by some number, and we can multiply 20 by another, and this combination must be equal to 4. So you may see, if you consider lambda as 2, then this will be 2 into 12, that is 24, and we should have to subtract this 20. 24 minus 20 is 4. So this is the combination for lambda here is 2 and mu here is minus 1. This again can be written in different ways. So we can write this also as say this 20 is multiplied by 2, then it becomes 40, and then we can have this as 12 multiplied by minus 3. Now you see, this is minus 36 and this is plus 40. So therefore again the result is 4, and the greatest common divisor is written as combination of these integers, again 12 and 20. That is the meaning of this lemma. Also we have studied this type of result in integers, that is in number theory. Now we shall prove it. So for this we shall consider the set A as all possible combinations of A and B. Let A be the set of elements of the form that is RA plus SB, where R and S range over R. That means R and S belongs to R. All possible combinations of A and B are considered. Combination of A and B means A is multiplied by some element, B is multiplied by another element, and they are added. So that is A is equal to, A is the set of elements of this type, RA plus SB, where RS belongs to R. And you see A, B are already in R. So all the elements A, B, R, S are in R, and the set of this type of element is denoted by A. Now what we shall claim is that this A is an ideal of ring R. That is our claim. A is an ideal of R. And we shall prove this claim. A is ideal of R. Now we know earlier that what is the condition for our definition of ideal of a ring. There are two conditions. First, A must be subgroup of R under addition, and second is let U belongs to R and any element X belongs to A, then their product is again in A. These are the conditions for an ideal. So first is A is a subgroup of R under addition. This we shall prove. And we know for proving a subgroup of a group, so it is only necessary that we shall consider X and Y are two elements in A, and then we shall prove that X minus Y is again in A, and that proves A is subgroup under addition. So let X, Y belongs to A. So why this is so? Because for subgroup A, B, if we consider two elements A and B in subgroup, then we need to prove A into B inverse is again in the set. Then it becomes subgroup. So we know from group theory H is subgroup of G. If A comma B belongs to H implies A into inverse of B belongs to H. That is A star. Here the operation is plus, and therefore here what we need to prove X and plus inverse of Y is negative Y, and that belongs to A, and that means X minus Y belongs to A. That we need to prove. And here we have considered X and Y belongs to A, and X and Y are elements of A, so therefore X and Y both must be combination of A and B, and therefore let X is equal to R1A plus S1B, Y is equal to R2A plus S2B. We have changed R and S. A, B remains fixed. R, S range over R, and that means here R1, S1, R2, S2 belongs to R. R1, R2, S1, S2 belongs to R. Now what is X minus Y? X minus Y, or that is X plus of negative Y, is equal to R1A plus S1B minus R2A plus S2B, and this can be written as, see how we can take these two together, R1 minus R2 times A plus S1 minus S2 times B. And certainly this is combination of A and B. R1 minus R2 are elements of R, and R1, R2 elements of R, R1 minus R2 is also an element of R, and because it is a group under addition. And similarly S1 minus S2 is an element of R, and therefore this is a combination of A and B again, and it is of this form. In place of R we have R1 minus R2, in place of S we have S1 minus S2, and this belongs to A, and therefore this shows that this is sufficient to show this A is subgroup of R, and thus therefore A is a subgroup of R under addition, under plus. Now second condition for ideal is let U be an element of R. We want to prove A is ideal of R. The second condition in the definition of an ideal is let U belongs to R, X belongs to A. Then we have to prove U into X belongs to R. And you see, this is commutative, and therefore if U into X belongs to A, we have to show U into X belongs to A. If U into X belongs to A, X into U also belongs to A, because the ring is Euclidean and it is commutative. Then U into X is equal to U is element of R. X, we take this the same element in A. X belongs to A, that is R1A plus S1B, and this can be written as U into R1 times A plus U into S1 times B. And again we see that this is a combination of A and B of this type, and this belongs to A. It is a combination element of this type, and therefore this belongs to A. Similarly, also X into U, these are commutative, therefore these are equal. The ring is commutative, belongs to A, and hence or thus A is an ideal. A is an ideal of R. This proves. Now once we have proved A is an ideal of Euclidean ring, earlier we have studied a result that Euclidean ring, an ideal of Euclidean ring is principal ideal, or it is generated by a single element, and thus there exists an element D such that every element of this ideal A is multiple of D. There exists an element D belongs to A in the ideal such that every element of A is multiple of D. This is a result that we have studied in our earlier lecture. If R is a Euclidean ring, then ideal of an Euclidean ring is principal ideal, that is, it is generated by an element in A, and or this can be written as, that is, A is generated by D, that every element of A is multiple of D. And now we have the element of A also in this form, RA plus SB, and D is an element of A. Therefore, this D element is of this form RA plus SB combination. D is an element of A. So we can write the element D we have D belongs to A, and therefore there exists some elements, some lambda and mu, such that D is equal to lambda times A plus mu times B. Because D is in A, D must be in this combination A of A and B. In place of R and S, we have taken lambda and mu. These may be different because lambda, R and S are not fixed, they range over R, and therefore for this D there exists lambda and mu such that D is equal to lambda A plus mu into B. Further, R is Euclidean ring, and in a Euclidean ring contains unit element. R is an Euclidean ring, contains unit element 1. It contains unit element 1. And therefore we can write 1 belongs to R. We have A is equal to, we can write A as 1 into A plus 0 into B, and that is a combination of A and B. 1 belongs to R, 0 also belongs to R, and thus this A belongs to A. And what about B? B can be written as, now we may verify 1 into A is A and this is 0, so A plus 0 is again A. B can be written as combination of A and B. And here we consider this multiple of A as 0 and multiple of B as 1. So thus B is equal to 0A plus 1B, and that is again a combination of A and B, and that belongs to A. Thus A belongs to A and B belongs to B. And we have, these are the elements of the ideal A. And now D divides A. D is every element of ideal is multiple of D. See, we have written there exists every element of A is a multiple of D, and therefore that D is divisor of A and D is also divisor of B. And being in A and B, A comma B, being in A are both multiples of A, multiples of D, and that means D divides A and D divides B. So this proves D is a common divisor. And what remains to prove is it is greatest common divisor. So, or we may suppose this as 1. Further, if there is another common divisor, that is C, C divides A and C divides B, then we have seen earlier in remark that C divides lambda times A. If C divides A, then C divides any multiple of A. That is the definition from divisibility. C divides lambda A and C divides mu into B, multiple of B. So that is easy to verify. Say 2 divides 6, then 2 divides 6 into any integer, say 3. Like this. And C divides B means C divides any multiple of B. So, and if this again C divides lambda A, C divides mu into B, C divides their addition, lambda A plus mu B. C divides lambda A plus mu times B. But what is lambda A plus mu times B? That is D. And this implies C divides D, and this is our second result. D is a common divisor. If there is any other common divisor C, then that C also divides D, and this proves D is greatest common divisor. D is the greatest common divisor, and D is written as the combination lambda A plus mu into B. Thus D is the greatest common divisor. And D is equal to and D is equal to lambda times A plus mu times B. So thus this proves the lemma. We have proved here for Euclidean ring R, any two elements A and B in R has greatest common divisor, and that greatest common divisor is written as a combination of A and B. So I hope you can understand these results. Thank you for watching the lecture.